All right, so as promised, we're going to begin this process of looking into detection and correction of errors in the least efficient way possible through the notion of a repetition code, which is maybe something that you're already having kind of in the back of your mind, is that if I'm going to send some message through a noisy or unreliable channel, why don't I just go about sending that message over and over and over again and hope that enough of them are unaffected so that the recipient can be like, okay, well, half of these things look totally fine, so I'm betting that's what the original message was. That's totally fine. It's going to work. So it's going to give us our kind of nice theoretical cap that's going to say that we can do this. The question then becomes, should you do it like that, or are there going to be more efficient ways or better ways that we can actually do this? And the answer to that question is absolutely. This repetition way is horribly inefficient and littered with any number of other issues, but it does kind of get the ball rolling. It also begins this kind of nice picture side of things so that we can kind of start to snowball this process a little bit. So down below, I have kind of a cheesy little picture. So the idea is that I'm going to have some letters. So here I'm just going to have the alphabet, and I'm going to send the letter M across this channel. So this channel, whatever it is, so this super duper secure question mark padlock channel is not so great in that only 90% of the time it's going to be successful, in that it's going to return an M. 10% of the time, it's going to return something else. So the idea is that maybe I send an M and it comes out as an M and I'm super duper happy, but I could have an M and I could actually receive an A, which is then problematic. Hopefully you can see that that's already pretty tricky to work with, because if I receive that singleton A, I really have no idea if that's what I wanted to receive. I don't have any things to compare it to. It's not like earlier when I actually had words that I could be like, well, that's not an English word, so that doesn't make any sense at all. Here I'm just left with this letter A, and I have no idea if that's actually correct or not. There's a 90% chance that it's good. There's a 10% chance that that's absolute rubbish. So the idea here is that rather than sending a singleton M, I'm going to begin sending multiple M's and then hope that most of them are unaffected. So if I were to send, let's say, 3 M's, so I'm going to hit MMM, send those triple M's across this noisy mystery channel with padlock for extra security, what you can see is that one of those things did in fact flip. The middle one changed from an M to an A, which is fine. We knew that one of them might actually go about changing. The other two were unaffected, so I can see the 3 letters. 2 of them are still M's. The middle one's an A, so I can go about actually assuming that my message was probably an M. And that's actually the reason why I went from having a single letter up to sending 3 letters. If I went to having just 2, so if I took my M and padded it with another M, and then I sent that thing across and it ended up as an M and an A, then I have no idea who's the majority. I have for sure a switch, but I don't know if the switch was the M to an A or if it was an A into an M. So the idea here is that I can improve it just a little bit by sending 3 M's, and then hopefully at most only one of them are actually going to change. So it's this cheesy notion of boosting that we then can begin shoving into this process. So we start off with this chance of 90% success. Well, if I pad it with itself a few more times, my chance of success is actually going to get boosted up just a little bit as well. So if I send the triple M across the channel, there's essentially 4 different ways that I can simply record that the message was an M. If I receive triple M's, my message was an M. If I receive 2 M's and then some other letter, then I know that the M's are the majority and things are totally great. The things that would then become problematic would be if I received 1 M and then 2 non-M's. So the M could be in the first one, the M could be in the middle one, or the M could be the last one, or it could potentially have no M's at all. Basically, all 3 bits did in fact change to something else. So if I simply record the 4 things that are quote unquote good, I can see the chance that those things are actually going to be received on the back end. So triple M's are going to come with their own probability. So a 90% chance of staying put, a 90% chance of staying put, and a 90% chance of staying put does in fact give me like a 0.9 cubed. So 0.9 times 0.9 times 0.9, which is like 73% of the time you're going to receive triple M. And then the other 3 are basically going to be calculated the same. There's going to be the 0.9s of keeping the M paired with the 0.1 of having something extra. So all of those are going to look like 0.1 times 0.9 times 0.9, and you got 3 copies of that. So what you can see is that my original 90% can then actually be boosted up to about a 97.2, which is kind of fun to play with. And if you go back to actually thinking about this, maybe some of our earlier Markov chain alarms are actually screaming at you, is that if I send an M and it stays in M, there's going to be some loop on an M with a probability of 0.9. If I have a non-M, it's going to move into another state. And then if I have two of those, then it's going to move into some form of a failure state. So what this is actually keeping track then is going to be this probability of starting in the M and then moving into some form of accepted state, which is going to come with a probability of like a 97.2-ish or so percent. So it's pretty good. It went from 90 up to 97 with only having to pad 2 extra things on it. And life is pretty good from there. So hooray. We can actually push this idea a little bit farther. So if I wanted to, let's say, send some messages that were length 2. So let's just play with bit strings. So there are only 4 bit strings of length 2. They are 00, 01, 10, and 11. So I'm going to send this thing through some type of channel. And let's just say this channel is guaranteed to switch at most 1 bit. So I'm going to assume at most 1 error. So the way that I do this is I'm going to take that 10 and I'm going to pad it with itself 2 more times. So I increase my length from 2 now up to 6, and I'm going to send this 101010 across this channel. The idea is that one of those bits can be flipped, and I don't care which one you flip. No matter which you flip, I'm always going to have 2 little blocks that both contain a 10. So if you flip that last 0 into a 1, you can see that I'm going to get 10, and I'm going to get another 10. So I can always record what my original message happened to be. So this notion of repetition does give me this approach of both detection and correction, because I know which one was in fact flipped, and I can actually fix that and tell you exactly what the original message was supposed to be. However, it's super duper wasteful because I'm taking this little 2-bit message and I'm turning it into 6 bits. And that's only allowing me to correct 1 single error. If I went up to trying to, let's say, have 2 errors, you're going to see that I'm going to need more padding to actually occur. Simply padding it with itself 2 more times, so increasing this to 3 copies, isn't going to be strong enough to actually detect and correct this error, because you could have this scenario that you had, let's say 10, and then maybe you flip that bit, so it becomes a 11, and then the other one becomes a 11. Well, if you zoom at this, you can see that those things then become the majority, so I would think that my message was actually 11. So we need to pad it with more stuff. So basically the additional amount of errors are always going to bring about more padding that you in fact need. So if I went from 1 error to 2 errors, what's going to happen is that I'm going to take that original 10 and I'm going to pad it with itself a whole bunch of times. In total, I'm going to have 5 copies, because when I have 5 copies, you can change at most 2 of them with your 2 errors. So 2 flips anywhere you want. I'm always going to have 3 versions of my original string. So if I have 1 error, I'm always going to create 3 of those things. If I have 2 errors, I'm going to pad it so I have 5 copies of that thing. If I changed it to having, let's say, 3 errors, you can see that this 5 copies is then going to change up to 7 copies. And that's where things begin to grow out of control. Is that if I have some message that's tens of thousands of bits long, and I'm assuming that there might be thousands of errors, that's a ton of padding. That's going to be absolutely massive and super duper inefficient for how we want to go about these things. But it is technically possible. So if you assume that there are going to be R errors, you're always going to send 2 R plus 1 copies of that particular message. What that tells me is that I'm always going to have a majority of unaffected copies in my actual received message. So I'm going to have, let's say, 101 things on the back end. Well, that's always going to tell me that 51 of them are then going to be unaffected and 50 of them might be affected. So that 51 is then always going to be the simple majority, which is then going to receive the votes, basically, is that we think that this message came from the thing 10, and then you go from there. So that's the idea of a repetition code. Basically, you take that same code and you just jam it up with itself over and over and over and over again. You push that super duper long thing through the channel. If you're allowing to have R errors, you go ahead and just say, well, change whatever ones you want to. I'm always going to have majority, so I can always tell what my original message is supposed to be. It's a nice starting place. It's obviously super duper inefficient in that the length of the actual message becomes obnoxiously long. And it's going to bring about a few other errors as well. But it does give us this kind of initial theoretical cap that we can do this. No matter what, I can just pat it with itself over and over and over, and I can detect and I can correct. But the amount of redundancies that I had to put into this thing were truly astronomical, and I really want to try to pare that down a little bit smaller. So that's what we're going to be working towards in the next little bit. So we're going to start off simply with the question of detection, and then we're going to go about actually chatting about detection and correction in the actual Hamming code. So we'll kind of start to see how these things begin to build on each other in a pretty fun fashion.